Starting off our third unit in AP Calculus, we're going to be focusing on using the first and second derivative to explore some different features about the original function. So today's video is going to focus on applying the first derivative test of extrema and using the first derivative test to tell where the function is increasing and where the function is decreasing. We've already accomplished this, learning how to take the first and second derivative of different functions. So, increasing and decreasing functions. The idea of an interval. So we're going to talk about an interval that's open, right? So parentheses rather than brackets, on which a function is increasing is fairly intuitive. It's like a car traveling up a hill. Or sometimes we talk about it like walking up a mountain or climbing up the part of the roller coaster. But what's happening is if you think of x changing from left to right, the function values, so the outputs, also get larger, then the function is increasing on that interval. So a function f of x is increasing on the interval from, we'll say, a to b, with writing it that b is greater than a. Okay, so we're reading from left to right. If f of b is greater than f of a. So all that means is if I have some interval from a to b, and I know that f of a is less than f of b, then my function is increasing from a to b. Okay, next one then, a function is decreasing would be just the opposite. So a function f of x is decreasing on the interval from a to b with b greater than a, if f of b this time is less than f of a. So if we have some function, and we've got a and we've got b, and get that blue line out of there, maybe. There we go. And we have f of a, oh, well, it wants to come back apparently. F of a and f of b. F of b this time is less than f of a. On that interval, then we would say that our function is decreasing. So increasing, walking up the hill, decreasing, walking down the hill. All right, so we always use open intervals, like I mentioned, open intervals when identifying increasing and decreasing, increasing, decreasing, and then your function also could be constant, where you just have a horizontal or a flattening out, right, where you're walking on flat ground. Well, the first derivative, since the first derivative represents slope, we can use the first derivative to help us figure out where a function is increasing, decreasing, or constant. So if f prime is greater than 0, that means that f prime is positive, then f, the original function, will be increasing. If f prime is less than 0, well, less than 0 means negative, then f is decreasing on that interval. And if f prime is perfectly equal to 0, even for a brief second, we would say that f is constant. So let's draw a picture to go with this idea. Just go ahead and sketch a graph that looks kind of like mine. Don't worry too much about it. And I'm going to go through and I'm going to highlight all of the places where f is increasing. So f is increasing until about there. F is increasing until there. Then all the places where f is decreasing, I'm going to put in red, decreasing. And then all the places where f of x is constant, so a brief 0, or maybe an interval of 0 are going to be in purple. So this part in green and this part in green, if we're talking about our derivative, our original function was increasing, which means that our derivative is greater than 0 or positive. Our derivative is greater than 0, positive, because derivative represents slope. Then anywhere I have my red interval, we would say that f prime is negative, because my function is decreasing, so f prime is negative. Well, f prime being equal to 0 has to happen between our positives and negatives, right? Because the only way to go between positive and negative values, or negative and positive values, is to have a brief moment of 0. This then also represents an interval where our slope is 0. But then we have one last little problem spot, and that little problem spot is right here that we haven't identified, right? We switch from positive, go through 0 to get to a negative, go through 0 to get back to a positive. It's like, how do we go from positive just magically to 0? Well, there could be some point that is not differentiable. In this case, we've got a cusp going on. So this is f prime is undefined, right? And that will happen when we have a discontinuity, or where we have something that's not locally linear, or where we have a brief moment of a vertical tangent. All right, so what is a critical number? Well, what does it mean to be critical? Critical is something important, right? If somebody is in critical condition, unfortunately, that means that something important is going on, right? Something has a critical deadline. It's an important deadline. A critical number for us is going to be anywhere that f prime is equal to 0, or where f prime is undefined. And that's because our derivative will be changing. Positive to negative, negative to positive, right? Or something with a 0. So in between those critical numbers is where we would define intervals of increasing and decreasing. A critical number is going to be where something important is happening. All right, so here's our official first derivative test for figuring out increasing and decreasing intervals. So when you see things on a calendar that mention a first derivative test, it's not an exam. It's using the first derivative to test for intervals. So step 1 is going to be taking the derivative. Then we're going to set the derivative equal to 0 and consider where the derivative is undefined. We're going to set up some intervals, and then we're going to do some derivative testing of those intervals. So what I'm going to ask you to do first is pause your video and take the derivative of this function f of x. All I need you to do is take the derivative, and I would maybe clean up your answer. So pause the video, take the derivative. Okay, here's our derivative. Check that off. Just swung the 2/3 down in front, left the inside alone, dropped the power, times the derivative of the inside, which is just 1, and then this negative 1/3 means it's a cubed root on the bottom. The next thing then is set the derivative equal to 0 and solve for x. So here's the derivative. I'm going to set that equal to 0. Okay, and then it also says consider if the derivative is undefined. So I want to see is 2 over 3 cubed root of x minus 3, is that ever undefined? Notice I don't set it equal to undefined because we can't be equal to something that is not defined. Well, solving this first purple one, I would multiply both sides by the entire denominator, and I would get that 0 is equal to 2. Well, that's never going to be true, so there are no critical numbers from setting the derivative equal to 0. When something is undefined, it's when the denominator is equal to 0. So if I think about where this denominator is going to be equal to 0, that's going to be when x equals 3. So 3 is a critical number. There is something important going on when x is equal to 3. Okay, so the next thing that we do then, according to our step-by-step checklist, these critical numbers define intervals. So on a number line, we're going to set up a number line and call that number line f prime of x. We're going to plot our critical number. Well, our critical number was x equals 3. What I've done then is I've created two intervals. I've created the interval from negative infinity to 3, and I've created the interval from 3 to infinity, right? I've chopped that number line at 3. It says test the sign of the derivative by plugging in a random number from each interval. So if I pick a number from negative infinity till 3, I'm going to test that number in the derivative. So I'm going to choose f prime of 1. Well, f prime of 1 is 2 over 3 cubed root now of negative 2, because 1 minus 3 gets me negative 2. Overall, this value comes back as a negative number, which means that this whole interval, it wouldn't matter what number I pick, this whole interval comes back negative. Well, then I'm going to pick a number between 3 and infinity. I'm going to choose 4. Well, this time 4 minus 3 is going to be 1. This whole number, well, it's not a whole number. That's a math joke. This number comes back positive, which means any number between 3 and infinity would come back positive. So it says the sign of f prime will tell you if the original function is increasing or decreasing. Well, based on what we found, on negative infinity until 3, f of x is decreasing because f prime of x, the derivative on that interval, is less than 0, or negative. The next one then, the other interval that we created, on 3 to infinity, f of x is increasing because f prime of x is greater than 0, which means that we have a positive slope. All right, so the last thing then, just to talk about, it doesn't ask you to graph this function, but I do want to remind you that this graph, which was f of x equals x minus 3 to the 2/3, is that bird graph that's been shifted to the right. So is it true that this part of our function is decreasing, this part of our function is increasing, and at this moment, our f prime is undefined? Why, yes, it is. And that's what our derivative test, our using the first derivative, found for us. We found a decreasing interval, we found an increasing interval based on the signs, S-I-G-N-S, of f prime. So I'm going to stop this video here. The next video is going to pick up just with 2 more examples going through. If you think you have the hang of it, you could try those 2 examples on your own. We're looking at this one, find the open intervals, and then this one, find the extrema. So I would maybe try those on your own and then compare answers. Those of you that took math analysis might feel more confident in trying those on your own, but definitely watch the second video with the examples. I'll see you in the next video.